Hi, my name is Joanna Holt. Today I'm speaking on behalf of the Dutch Black Hole Consortium. I'm a science education researcher based in the Smart Education Lab of the Amsterdam University of Applied Sciences, and my research interests focus on primary level science education. Alongside this role, I also work as the Education Manager for the Netherlands Research School for Astronomy, and I'm the chair of the NAEC team for the Netherlands. Before moving into education and outreach roles 10 years ago, I worked for many years as an astrophysicist. Today I'm going to be talking about the Dutch Black Hole Consortium education programme. I'd like to start this presentation with my take-home message. The Dutch Black Hole Consortium comprises a group of more than 30 scientists carrying out interdisciplinary research in the Netherlands. The collaboration is extremely broad, including astronomers, theoretical physicists, engineers and telescope developers, geologists, seismologists, and education and outreach specialists. And whilst at face value the topics sound unrelated, all are necessary to further our understanding of black holes. Another crucial aspect that makes this collaboration unique is the emphasis on education and outreach. Whilst education and outreach is often an add-on in many projects, a third of the work effort and budget in the Dutch Black Hole Consortium is dedicated to disseminating black hole science to both the wider public and to educating and inspiring the next generation of scientists. The Dutch Black Hole Consortium has funding initially for 6 years and officially started work in September 2021, so you'll be hearing plenty more in the coming years. More information about the consortium, its members, work packages, meetings and regular updates on progress can be found on our website. Here I list the various partners and show a geographical distribution of their locations. The collaboration includes various departments from a number of Dutch universities and the education, teaching and research departments of 2 universities of applied sciences. Various research institutes also participate, including the Seismology Department of the Royal Dutch Meteorological Institute, the KNMI, NICEF, the Dutch National Institute for Subatomic Physics, ESRON, the Netherlands Institute for Space Research, and the Geological Survey of the Netherlands based at TNO. The consortium also includes 2 science musea in Leiden and Kerkrade. Finally, a number of other partners include companies, the Las Cumbres Observatory, and the province of Limburg. The Dutch Black Hole Consortium also cooperates with the Harvard Black Hole Initiative and the physics educational website natuurkunde.nl. So we've had the executive summary, now let's dive into the details. I'd like to start by explaining to you a little about the various sections of the project, particularly focusing on the links between the various work packages. As I mentioned on the previous slide, the consortium and work covers a broad range of topics, and I will outline these using the different work packages. The first few work packages focus on astrophysics. The astrophysics effort includes work related to black hole imaging and modelling and the progenitors of gravitational wave events, both from an observational and theoretical perspective. The next work packages focus on research and development work necessary for the Einstein telescope. For those that are unfamiliar with the Einstein telescope, it is a new gravitational wave detector that will be built within the next decade. One of the possible sites is the very south of the Netherlands, straddling the border with Belgium. The Einstein telescope will be much more sensitive than current gravitational wave detectors, and in order to achieve this, new technologies need to be developed. The Dutch Black Hole Consortium will develop new mirror technologies required for the telescope design. Another issue is the location of the telescope, which will be situated a few hundred metres underground. The telescope is huge. Imagine an equilateral triangle with sides 10 kilometres long, with large chambers at each vertex. It's important to know the geology of the area very well to know whether it is possible to build a telescope in this area and, if so, with which orientation and at which depth below the surface. The Dutch Black Hole Consortium also includes geologists and seismologists working on improving our knowledge of the geology of the potential site. Part of the enormous education and outreach effort lies in the collaboration with 2 science museums in the Netherlands. As the region in the far south of the Netherlands is one of the key contenders for the location of the Einstein telescope, the consortium felt that it was important to have a strong education and outreach present in that area of the country. The consortium is creating new content for the Discovery Museum, an interactive science centre with an inverted full-dome theatre. The flagship content will be a modular planetarium film to explain the science and technology of the consortium. An exhibit outside of the theatre will expand on the topics in the film, and a small pop-up exhibit is already in place. In addition, we are working with Boerhaave Science Museum in Leiden. In the second half of the work period, so from around 2024, there will be a large exhibition about black holes, including the history of black hole imaging. And finally, the educational projects at the heart of this collaboration. But before we move on to the main topic of this talk, the formal education programme, I just want to give some details about the Citizen Science project with BlackGEM. BlackGEM is a Dutch optical telescope array based at the European Southern Observatory in La Silla, Chile. BlackGEM currently has three 65cm telescopes which, working together, have a field of view of 2.7 square degrees. That's almost 13 times the area of the full moon on the sky. Its goal is to identify transients in the night sky. And the main goal is to look for counterparts to gravitational wave detections at optical wavelengths so that these sources can then be followed up by larger telescopes. These telescopes generate an enormous amount of data, and the BlackGEM team estimate that around 100 million sources will be observed per night, including many transients of all types. Whilst automatic detentions come so far, human interaction is always necessary, and so a large citizen science project is being developed. For the detection of gravitational wave counterparts, speed is of the essence, so that larger telescopes can be scrambled to perform follow-up observations. This is why the data will be ready incredibly quickly. Within 20 minutes of the initial observation, the data will have passed through the calibration pipeline and will be available to citizen scientists. The test version is expected to be ready in early 2023, with a public version late in spring. The project will initially be available in Dutch and English, with more languages to follow. But now I want to focus on the education package, and as you can see from this diagram, it sits right at the heart of the project, with all other activities connecting into it. Another key point is that budget-wise, the 4 education and outreach packages account for a third of the total budget, highlighting the importance of this work within the collaboration. So what does the education programme include? Firstly, a lesson package is being created for upper primary level, or 10 to 12 years old. This is being developed by the Smart Education Lab of the Amsterdam University of Applied Sciences and focuses on practicing scientific thinking through hands-on, minds-on learning. The materials will be thoroughly tested in primary schools and at the affiliated Primary Teacher Training Institute and will answer science education research questions. Modified versions of the activities will also be made available for the educational programmes of the Musea in the consortium. Once the package is ready, it will be distributed through the various networks, and I will give some more details about this later in the talk. The second goal of the education programme focuses on trainee secondary school physics teachers. The consortium will offer research internships to these trainee teachers. And the idea is to give them experience of real scientific research and help them later convey what it really means to be a scientist to their future students. The first internships have already started. Finally, the consortium wants to investigate the impact of the educational programmes in both formal and informal settings. This study will provide important information for discussions at high level aimed at improving the visibility of cutting-edge science in school curricula and lesson materials in general. As with all elements of the interdisciplinary consortium, everything is interlinked. So how can we present this in a clearer way? Starting with the lessons for upper primary school for 10 to 12-year-olds. They will draw on the scientific and technical work packages for inspirational topics with which curriculum topics can be linked. The lessons will then be tested in schools and during primary teacher training. The research internships will also work closely with research and technical groups, and the internship programme will be researched and be the topic of a PhD project. Experiences from the research internships will also feed back into the primary lessons. As I will discuss later, the primary lessons will not only focus on scientific concepts, but also on scientific thinking and scientific attitude. The lesson activities will also be modified for use in the educational programmes of the museums and possibly also be offered alongside the Citizen Science project. And the impact of the educational programme in both formal and informal settings will also be researched by a PhD student. In the last part of this talk, I want to tell you a little bit more about the primary lesson package, as this is the part of the project that I will be working on. So what do we want the lessons to be like? The goals for the primary lessons are as follows. We want to tackle relevant primary science goals and to help children think scientifically and assist teachers in this process. We also want to inspire children to be the scientists of the future. And we want to do this by using the exciting context drawn from the cutting-edge science and technology within the consortium. But this is going to be a major challenge. The first challenge when it comes to primary science in the Netherlands is getting it done at all. Science is only recently a required subject in primary schools. Even so, many schools do little science. Reasons include teachers not feeling that they have the right skills to teach and discuss science, and this is exacerbated because there is no compulsory testing in science at the end of primary school. Because compulsory science education in primary schools is relatively new, the primary curriculum is not particularly well defined. Science falls under sciences and humanities in a broader subject area, roughly translating to world orientation. Within this area, a number of final learning goals are defined. On the slide, I show 2 learning goals most relevant to this topic area. Number 46 is focused on astronomy, with an understanding of the Earth, Sun, Moon system at the centre. Number 42 looks at investigating various physical processes, including light. Unsurprisingly, black holes are not mentioned. For those who are interested, there are also a couple of learning goals related to technology, but the ideas covered are fairly basic. In addition to the list of learning goals, the Dutch Primary Science Guidelines include this diagram for use by primary school teachers. It defines science education as being an equal mix of 3 areas: knowledge, attitude to learning, such as the drive to want to understand, to collaborate, and to work critically and innovatively, and science skills. And a number of elements fall under science skills, such as understanding how to set up an investigation, but also the individual skills required to be able to carry out such an investigation, such as observing, measuring, using tools and materials, and most importantly, scientific thinking, both in terms of thought processes and reflecting on what you have done. As you can see, the blue circle is enlarged with a paler blue circle, as many of these scientific skills call on skills from other areas such as language, maths, and the so-called 21st century skills like problem solving. All of these elements are embedded in the context, the green circle, and to get the best learning outcomes, it's necessary to choose a context wisely. Context which children find exciting, but also linked to the experiences of the child. This can be through previous experience or by using more hands-on activities so that children can discover for themselves. As you may have noticed, the learning goals I showed in the previous slide are fully focused on the knowledge of science concepts and processes. And this is typically how science is taught in many primary schools, as bookwork. This is most certainly related to the fact that the learning goals and learning paths for the attitude and scientific skills are even less well defined than for the knowledge. But the blue and pink circles is where much of the development in primary science education research is focusing. It's a key focus for science education training for trainee teachers and is also particularly interesting for this project. The main focus of this project is to work towards improving children's scientific thinking skills by working on the so-called cross-cutting concepts. Cross-cutting concepts are a way of thinking about science which are applicable to many different concepts, such as cause and effect relationships or thinking in systems. We want to combine this with another key idea, hands-on, minds-on learning, the so-called generative learning model. The lessons will aim at teaching key curriculum topics, whilst drawing on the cutting-edge science and technology from the broader Black Hole Consortium for an exciting and inspiring context, to motivate children to learn and to understand. The learning of scientific vocabulary will also play a key role. The lessons will build on the experiences in the Minds-On project, a project which has been running for the last 2 years at the Smart Education Lab at the Amsterdam University of Applied Sciences. As with this project, the goal behind Minds-On is to promote the understanding of scientific concepts and reasoning skills and stimulate hands-on, minds-on learning. The lessons include small practical activities and a brand new interactive digital tool. In the tool, learners recreate a concept map in steps, each step linked to the practical activities. Learners receive automated feedback to stimulate the thought process. I'm now going to show you an example lesson from the Minds-On project, which focuses on the seasons, to give you an idea of what the lessons in the Black Hole Consortium project will look like. Learners perform a series of short, interlinked practical activities to investigate how the sunlight falls onto the Earth, what effect the Earth's rotation has, and how does the position of the Earth change throughout the year, and what influence does this have on the illuminated area. After each practical activity, learners reconstruct the part of the concept investigated in the interactive digital tool. When necessary, the learners receive automated feedback. In this particular lesson, the cross-cutting concept is cause and effect relationships. This is what the full concept diagram looks like. Learners only see this once all of the steps have been completed in the lesson and the diagram. The concept has been stripped down to the most essential subconcepts in order to understand the main concept. The information in the diagram is coded. The different shapes represent different ingredients. Circles are objects, heptagons represent movements, rounded rectangles are changeable properties, diamonds are values, and the dashed boxes denote groups of changeable values. The arrows show the relationships, from basic relationships in grey to cause and effect relationships as bold arrows. The diagram is built up slowly, each part relating directly to a practical activity. For example, learners will begin by filling in the section related to the Earth having a round shape after studying a small globe. The lessons and interactive tool have been through multiple testing and development steps. In each step, we have implemented changes based on the results from classroom testing. Changes included the precise ordering in the diagram, the way in which we represent changing values, for example day length and seasons, and which vocabulary is the most suitable for the age group. Classroom testing has been positive. All lessons created so far have had a measurable learning effect measured by pre and post tests, and the learner experience surveys show that both learners and teachers enjoy the lessons and feel that they help learners to understand the concepts. So I've talked about why this project is interesting, both from the perspective of the Black Hole Consortium and from science education research, but I've not really answered the question of why we should be bringing black holes into the classroom at all. As I mentioned before, black holes certainly don't feature in the curriculum. Black holes are also not tangible. Children can't do experiments with them, and they don't relate to children's everyday surroundings. This is where my other role comes in, as Education Manager for the Netherlands Research School for Astronomy and responsible for the NOVA mobile planetariums. We already know that astronomy topics are some of the most interesting science topics for both boys and girls from studies like the ROSE project. But just from practical experience, there is one thing that happens without fail in every single lesson in the planetarium. With 4-year-olds, with 18-year-olds and everyone in between. The one question that comes without fail is, can we see a black hole? So black holes provide the context to build the lessons around. To give you an example of science activities revolving around a non-curriculum topic, a very popular research activity in primary science lessons in the Netherlands is to do research on which are the best paper nota. Now, paper nota are the traditional biscuits eaten in November and December in the Netherlands. But children don't need to learn about them, but it does provide a context in which to build science skills. So to sum up, the Black Hole Consortium will provide the context. Black holes may not be in the knowledge part of the curriculum, but topics relating to black holes such as light and gravity certainly are. And the lessons will also focus on scientific skills and scientific thinking and motivation. So to finish off, I'd like to remind you of my take-home message. The Dutch Black Hole Consortium comprises a group of more than 30 scientists carrying out interdisciplinary research in the Netherlands. The collaboration is extremely broad, including astronomers, theoretical physicists, engineers and telescope developers, geologists, seismologists and education and outreach specialists. Whilst at face value the topics sound unrelated, all are necessary to further our understanding of black holes. Another crucial aspect that makes this collaboration unique is the emphasis on education and outreach. Whilst education and outreach is often an add-on in many projects, a third of the work effort and budget in the Dutch Black Hole Consortium is dedicated to disseminating black hole science to the wider public and to educating and inspiring the next generation of scientists. The Black Hole Consortium has funding initially for 6 years and officially started work in September 2021, so you'll be hearing plenty more in the coming years. For more information about the consortium, its members, work packages, meetings and regular updates on progress, you can look on our website. And if you'd like to know more about the education projects in particular, please feel free to email me. Thank you.